Coming up on this episode, we're going to look at the sun, but not with our eyes because we don't want to go blind. We're going to look at it safely with NASA scientist Dr. C. Alex Young of the Goddard Space Flight Center. And he's going to tell us what's the deal with all of those solar storms, how they make auroras, what's the deal with those solar flare-ups, and no, not that rash that you haven't wanted to talk to anybody about. So tune in and let's get to it.
Podcasts you love.
From people you trust.
This is TWiT.
This is This Week in Space, episode 63, recorded on May 26th, 2023. The Angry Sun with Dr. C. Alex Young of NASA.
Listeners of this program get an ad-free version if they're members of Club TWiT. $7 a month gives you ad-free versions of all of our shows, plus membership in the Club TWiT Discord, a great clubhouse for TWiT listeners. And finally, the TWiT Plus feed, with shows like Stacy's Book Club, The Untitled Linux Show, The Giz Fizz, and more. Go to twit.tv/clubtwit. And thanks for your support.
Well, hello and welcome to another episode of This Week in Space, the Angry Sun edition. Don't look directly at it. I am your host, editor-in-chief, Tariq Malik, editor-in-chief of Space.com. Rod Pyle is off this week. He's speaking at the International Space Development Conference in Texas, hopefully finding out how we're going to deal with the challenges of space weather in the future. And he was smart enough to leave me in charge, which means that I get to pick the episode, and we're going to talk about the sun, space weather, and how it affects all of us. And joining us today is my very special guest and longtime friend, Dr. C. Alex Young, a solar astrophysicist and the Associate Director for Science at the Helioscience Division of NASA's Goddard Space Flight Center in Maryland. Alex, thanks so much for joining us today.
Hey, it's great to be here. It's been a long time since we've chatted.
It's been a long time, but hopefully we don't have to wait till another Solar Max to get together. And I've got questions for you about all of that. But first, as always, we have to start with a space joke. And I picked a good sun one. If you want to humor me here for a minute, Alex.
Sure.
Too. So Alex, did you know about the sun's favorite Queen song?
No, what is it?
It's Another Sun Bites the Dust.
Is this like the dad joke?
I got a rim shot and not crickets this time. Yeah. So it is always a very punny joke that we start with. Sometimes it's subject specific like today. And as always, dear listeners and viewers, we invite you to join Rod's Raiders and send us your best or worst space joke. And don't forget to do us a favor and go ahead and like and subscribe and all that cool podcast stuff. It helps us a ton, and it's free. So that's great. And so, Alex, this is the part where we talk about headlines really quickly for the week. Feel free to chime in if you have an interest. You know, the first one actually comes right hot off the presses from the day before we recorded this podcast. Virgin Galactic reached space with Unity 25. So basically, to kind of catch everyone up, Virgin Galactic is Sir Richard Branson's space tourism company. They've got plans to launch, thousands and thousands of people to the edge of space. Well, not the edge of space, to suborbital space and back on a space plane called a Spaceship Two. And for the first time in 2 years, they launched a crew of 6 people to suborbital space. And for them, that means about 50 miles up. There's some debate between, did they really reach space going 50 miles up, which is what the military classifies as space, or should they have gone to 62 miles, which is the more generally accepted boundary for space. But either way, they say that they went to space. They use an air launch system, the Spaceship Two Unity, that they carry up to about 50,000 feet with this giant carrier plane called White Knight 2. And this one is named Eve after Richard Branson's mother. And they basically were able to prove that their spacecraft is ready for flight, ready for commercial service. And it's been a long time coming. They're several years behind schedule. I think Richard Branson said once they would try to go around 2007, and here it is, 2023. And but they said it was a success. So they launched a crew of 4 people, 2 astronaut trainers and 2 engineers, and then of course the pilots themselves. And it was a by the book mission. It seems like everything seems to have gone swimmingly. And this now sets the stage for their first commercial mission, which will be, I believe, a flight for Italy, some Italian customers in late June. And so we're going to have to keep an eye on if they're able to stick to that. But that's the first flight since Richard Branson launched on this Spaceship Two back in 2021. And so it seems like it all went good. So that's a nice big achievement for them. So we wanted to make sure that we highlight that. The next big story in our roundup. Would you ride on Spaceship Two, Alex, by the way?
I absolutely would.
You would?
Oh, totally.
Yeah?
I would love to orbit the Earth a couple times, maybe, or maybe even go to the space station. I don't think I want to go any farther than that, but that would be awesome.
I don't know if I would trust myself to like unbuckle from the seat. You get I didn't mention this, but you get 4 minutes of weightlessness. So like it like pushes you back, it goes straight up. Then you get 4 minutes of weightlessness. Then you got to get back in your seat and snap yourself in. I don't know if I'd be able to do that, but I guess they train. That's what the astronauts are going to train them to do.
Exactly. So. Yeah. I'd give it a try if I had the opportunity.
Yeah. So, well, if you do, please let us know. We'd love to hitch along
Absolutely.
for that. Well, next up is actually another thing from space. We got an alien signal from Mars this week, and this actually comes from SETI, the Search for Extraterrestrial Intelligence, the institute there. They actually conducted what they call it's a first contact sign in space experiment this week, where they worked with the European Space Agency's ExoMars project, and they beamed an alien signal back to Earth so that scientists could practice decoding a signal as a way to rehearse what happens if ET really did call us. And it seems just kind of like a really fun project. It's kind of part art. It was dreamed up by Daniela DePaulis, the artist in residence at the SETI Institute and the Green Bank Observatory, to basically get this signal from ExoMars and then kind of put it through its paces to see, like, can we decode it? What would that be like? Is it going to cause a big sensation like in the book and film Contact, or is it just going to be like and we're going to move on to, I guess, like the next big thing that's trending on social media? But it was an interesting kind of project that they treated it more art than science at the same time. And SETI is trying to find a lot of different ways to showcase how transformative detecting a signal from space that is of true alien origin would be, and I thought this was a really fun one to talk about today. Have we gotten any signals from the sun, Alex, like this? So. Well,
nothing that's not nature related. Nothing alien as far as we know.
But lots of fun.
It's a little hot there, so I don't know if we're going to find much there in terms of life.
Yeah. Well, maybe if we go in winter, right?
That's true. Yeah. Or at night, maybe.
That's right. Those are two new dad jokes that everyone just got for free. So, well, just big congrats to the SETI team and Green Bank Observatory, which is in Virginia, not very far from where I am, and I would like to go and see what that's like too. And then finally, rounding out our trio of non-sun stories this week, although I guess it could be somebody's son. There is a new supernova in the night sky that readers, you can all, if you've got a telescope, you can look for it yourself. It's in the Pinwheel Galaxy, and it was just discovered just like in the last week, called supernova 20. I'm going to get this wrong. Supernova 2023 IXF, so 2023 IXF, I believe, and it's located 21 million light years away from Earth. And like I mentioned, in the Pinwheel Galaxy, and it was discovered by an amateur astronomer in Japan who looks for these things and was able to find it, and then it was confirmed by astronomers elsewhere. And it's been sitting my space Twitter abuzz recently because a lot of amateur astronomers are just posting their photos and of what it looks like, and it's not that rare to have a new supernova. We found out today that there's scientists discover maybe 20,000 supernovas a year. This one stands out because it's the brightest in 10 years that scientists have been able to see, and so it's a star just in the act of I guess it's sad, right, Alex? It's a star in the act of dying.
That's right. That's right. It's reached its end. Or at least it's transitioned to something new.
Well, every end, right, is the start of a new beginning.
Exactly.
And so this is, it's important not just for the amateur astronomers who can, look up and find it with their telescopes, but I would assume anyone that studies stars, Alex, like yourself, would be excited to kind of see this stage in real time, in the night sky, to be able to track it over time to see how it develops. Is that right?
Absolutely. I mean, that's one of the greatest things about, if you like the sun and you want to learn about it, one of the best ways to learn about its past or its future is to look at other stars and see what happens to them. And, we're only stuck with what's happening right now, and it lasts for billions of years. So we have to look to other stars to get a bigger picture.
And I guess I should probably have that caveat that it is 21 million light years away. So the supernova explosive light that we are all seeing in these telescope pictures did happen 21 million years ago, I suppose.
Yes.
And so for the folks that live in the 2023 IXF system, I'm sorry for your loss of your son, but I hope that everything's okay now. So, and speaking about the sun, I think it's about time to start talking about that, and we will come to that right after this. Well, Alex, thank you for humoring there for both my corny jokes and the week's news. But we brought you here to talk about maybe a star more closer to home, our favorite star, the sun. And if you could start off with giving our listeners and viewers a bit of a primer about who Dr. C. Alex Young is, how you found yourself, focused on a star that's near and dear to all of our hearts, and I guess pretty key to life on Earth.
Sure. It's kind of a windy story. I mean, like a lot of people, I became interested in science as a young kid. I mean, at the age of 10, decided I wanted to be an astrophysicist, even though I didn't really know exactly what an astrophysicist was. But I was really inspired by science fiction. I mean, you may look around, you see Darth Vader and the Enterprise. I was inspired by those, but I was also inspired by the science that was going on. Cosmos with Carl Sagan was really big around that time, the beginning of the space shuttle program and the Voyager flybys of the outer planet. So all of those together kind of sparked a lot of my excitement and interest in science, specifically astronomy. Got my first telescope, saw the Galilean moons around Jupiter and the rings of Saturn for the first time, and then worked my way through, focusing on science and math and physics and mathematics. Went to undergraduate, got a degree in physics at Florida State University. Then I went to graduate school actually to study chaos theory, and particularly quantum chaos. But I did a summer project working for the Compton Gamma Ray Observatory, one of NASA's former great observatories like the Hubble, looking at the most energetic things in the universe, including supernova, gamma ray bursts, and finished up a master's. And my advisor said, hey, there's a lot of really exciting things happening on the sun. It's close by and we can see all this great detail and do all this amazing stuff. So are you interested in kind of shifting for your PhD? And that led me to my first job at NASA as a contractor. And 10 years later or 12 years later, I became a civil servant. And then here I am.
Wow. It's funny. It's funny how that works. My first internship was for the astronomy department at USC, and it was working for a helioseismologist.
Oh, really?
That's
like,
cool. Yeah, Ed Rhodes with earthquakes on the sun, which I guess they're not called earthquakes then. But it's like that one introduction puts you on that road to, I guess now, like the sun is like is like front and center all the time for you.
Exactly. And, everything, I guess that's the exciting thing about a lot of people in science is, none of our journeys are really straight. And it's getting to see lots of different things. And, if having an advisor who recognized some cool stuff and pointing me to it has led me to a pretty exciting field. And it is a really good time to be a solar physicist.
Yeah. So let's talk about that field, right? Because of course, director of science for the Helioscience Division at NASA. I thought, the sun, it comes up every day, it goes down every night. That's all there is, really to it. But what is helioscience really? Like, what do we know about the sun and its weather? Like, why should we really all care more than the fact that it brings us light and warmth during the day?
Well, I mean, the sun has been it's been obviously a part of society for thousands of years because, as you say, it's all, it's there. It comes up every day. People can count on it and our lives depend on it. But it also, in looking at it, studying it, and trying to understand it, has been part of the development of modern astronomy. And some of the key things in modern astronomy come from studying the sun, studying eclipses, and over the years, we've become to realize that the sun not only provides us light and heat, but it has a huge influence on everything in the solar system. And it produces, huge explosions, releasing lots of energy, lots of material, magnetic fields, and all of that stuff that's coming off of it interacts with planets, it interacts with other objects in the solar system, and now it interacts with everything we put into the solar system, like our spacecraft and our people. And so that has led us to studying what this influence is, and then getting back to the fundamental physics of why it happens in the first place.
Now, when I think of the sun's weather, solar weather affecting Earth, I think auroras. There's been a lot of talk about, I guess I saw a headline about, could the auroras come to all 50 states? Because there have been some storms, I suppose, that have been amplifying them over time. But it sounds like it's more than just supercharging the northern lights at the poles for Earth. Like what are those effects?
It is. I mean, that's certainly the most obvious way that we've seen it. And, the northern lights and the southern lights have been a part of society and history. They've woven their way through myth and through legend and lots of societies, especially ones in, like Scandinavia and places like that. And some of the scientists, especially those who did study aurora, helped to make these connections and realizing that there's a lot of other things going on. And I know we'll talk about this later, but there was even this huge event called the Carrington event. Mm-hmm. And not only was that one of the biggest events, in modern history, but that's when we started to make that connection for things are happening on the sun. And then all of a sudden, not too long later, we see things happening here. And what we've come to realize is, that impact that creates the aurora by, creating all these electrical currents in the upper atmosphere also changes the upper atmosphere. And that has huge influence on communications, on our ability to use things like GPS or shortwave radio, because those layers, these upper layers of the atmosphere, are electromagnetic in nature. They respond to radio waves. And those changes, the same changes that create aurora, are changing the environment, which is changing the ability to use a lot of these different types of communication. So that's the beginning, but there's certainly a lot other things that are happening.
And I guess as a primer, so like a storm erupts on the sun, a flare or an eruption that flings solar plasma, electrically charged particles out, I guess, just away from the sun. Mm-hmm. And if the Earth is in the way of that storm, it gets captured by our magnetic field and it funnels it to the poles because of the field. Is that? Please stop me if I'm wrong, because I'm trying to explain it.
Yeah, no, that's close. So the Earth, one of the things that's important about it is, and the key things that you need, for example, for the aurora, is you need the magnetic field. Mm-hmm. In particular, you need the atmosphere, because that's when all of this stuff interacts with the atmosphere. That's what is ultimately glowing, giving us the aurora. But the sun creates a huge eruption. Part of that eruption, it's a release of magnetic energy called a flare, which is just light. It's electromagnetic radiation over the whole spectrum. But it also often throws off a huge blob of solar material, and it carries with it its own magnetic field. And that blob, we call it a coronal mass ejection, as you mentioned, hits the Earth's magnetic field, and it shakes it kind of like a bell. And what happens is the Earth's magnetic field is very extended because the sun's material actually flows off constantly in something called the solar wind. So those are, particles that are smaller, less dense particles that are flowing off all the time, and they stretch that magnetic field into kind of a teardrop shape. And what happens is when all of this stuff comes and disturbs the magnetic field, all of this solar material that has accumulated at the far end of the magnetosphere, we call it, travels into the poles. And that gives us the aurora. Now, sometimes the material from the sun can directly funnel to the northern and southern poles, but typically it comes from the back part of the magnetosphere. And that's the beginnings of what we call a geomagnetic storm, an Earth magnetic storm created by the sun.
Wow. See, I should know better by now, Alex, not to spaceplane auroras to a solar physicist. So a solar astrophysicist. Well, that's amazing. Have you ever seen the Northern Lights yourself?
I have. I saw them when I was in graduate school, but it was in New Hampshire, which is a good place to be, but they were still really in the distant. They were just the glow. But where I've seen them up close and completely, over top of me, the very dynamic aurora is in Iceland. And it is quite spectacular. The first time I saw that, I knew it was going to be exciting, but I really wasn't prepared for how amazing it was.
Is it strange that a phenomenon like that lights up the night sky, originates from the sun, that we associate with the day?
It is. I mean, that's the interesting thing is people, we think of the sun during the day. We don't think of the influence, but this is an example of how it's influencing us all the time. No matter which way the Earth is facing, this space weather, this energy and matter from the sun can impact the whole Earth, the whole globe. And so it is a global phenomenon.
Well, so we were talking about the sun is always there doing its thing, not just, during the day. And there have been reports, I mentioned one of them about, how the sun's really super active. And so the auroras could reach all the states. There have been a lot of reports of flares in the last week or so from the sun. I was hoping to kind of get an idea of what's going on. You mentioned just before we started this call that solar maximum or whatever that is coming up. So what's happening right now? Is the sun just waking up, or should we have expected this to happen? Or
well, we expected this to happen. The sun, I guess the best analogy is the hurricane season. I mean, the hurricane season is a year long and related to the seasons of the Earth. And we always know that when we get to September, October, November, we're going to have an increase in hurricanes. And so that's a cycle that goes up and down on a yearly scale. And the sun has its own cycle, but it's much longer. So going from very low activity, which we call solar minimum, up to high activity, solar maximum, back down to solar minimum is roughly 11 years. So from minimum to minimum is roughly 11 years. Sometimes it's a little bit shorter, sometimes it's a little bit longer, and sometimes the strength of it is higher and sometimes it's lower. And that is directly related to sunspot number. Sunspots are where a lot of this activity comes from because there are concentrations of magnetic field on the sun, and that is the energy source. The sun's energy is converted to magnetism, and that is then converted back into energy, which is creating this. And right now, we're on our way towards the peak. Scientists, every solar cycle, and we started numbering them years ago when we had confidence that people were counting sunspots and had good estimates. So now we're on solar cycle 25, and scientists always make an estimate of what's the next solar cycle going to be like? How strong is it going to be? And when is it going to occur? A little bit before, a little bit after. So the estimates were that we were going to reach solar maximum probably around the mid to end of 2025. However, one of the exciting things is actually a colleague of mine, two colleagues of mine, one here at Goddard and one at HAO in Colorado, have come up with a new model describing the solar cycle. And it's almost like a clock. And what they have been able to provide what appears to be a much more accurate prediction, because the original prediction that was provided by NASA and NOAA by a panel of scientists actually has been overtaken by reality. So the sun has become much more active than the original prediction said. Their prediction includes this, and it also says that the cycle is going to be stronger than the scientists said before. Wow. So we may actually see solar maximum come next year, and it may in fact be bigger than the last cycle, because we expected originally that the two cycles were roughly the same.
Mm-hmm. So you mentioned that it's 11 years, so it's a longer cycle. But what makes it 11 years? Do we know? Why?
Well, yeah, that's a great question, and we don't know. We really don't know. Now we actually know that all stars have a solar cycle, have a stellar cycle. Some stars have shorter ones. Some stars have longer ones. And even some solar-like stars have slightly different cycles. And right now, we have some basic understanding of the physics of what's generating the magnetic field and how it changes. But our models do not specifically tell us why it's 11 years or even show that it's 11 years. We kind of have to tweak them to get them to match up. And so that's one of the big mysteries. Why is it 11 years and not something longer or shorter? And right now, we don't know the answer to that.
And you said sunspots count is like a sign.
Yeah, it's a proxy, I guess, is how we look at activity, you know.
But sunspots are weird in and of themselves, because, I mean, many people might be surprised to know that the sun even has spots. And as I understand it, they're regions they're cooler, but they're like super intense with this activity. Is that right? I mean, how can they be both cooler, I guess, than the rest of the year, which is what makes them?
Yeah. So it's the reason they're dark is a matter of sort of relative temperature. Now, the surface of the sun, the visible surface, we call it the photosphere. That's where the visible light comes from, is roughly about 6,000 Kelvin, or that's roughly 6,000 Celsius, which would be about 10,000 Fahrenheit. And that is the temperature, the normal temperature of the photosphere. But the sunspots, which come up underneath the photosphere and rise up, are darker because they're about maybe 4,000 instead of, you know, so they're still really hot. Yeah, they're still really hot, but they're cooler than the surrounding. So what happens is when you focus on the sun, you know, we can only see so much, you know, intensity range. If you actually focused on the sunspot itself and zoomed in, you would see that it's still very bright. It's just not as bright as the surrounding material. So when we look at them together, they appear dark.
Great. Well, I have a big sunspot question for you coming up next. But before that, let's just take a real quick break, and then I'm gonna, I guess, get the sunspot on. So let's do that real quick. Great. Well, Alex, thanks so much for that big primer. Now, I did have to ask, because we were talking at the space.com team earlier this week about this new, I guess it's not a new sunspot, but it's a ginormous sunspot that some amateur astronomers were talking about. It's called sunspot AR. I think that's active region, right? 3310 on the sun. And the folks over at spaceweather.com have this great image from amateur astronomer Bum-Suk Yum from South Korea, where he shows this giant sunspot. And I think we've got the photo, and it's like 4 Earths high, and there's like a little picture of the Earth to scale, and it really put it in perspective how big these places on the sun really is. And this astronomer was saying that they, with protective glasses, they could see it with their own unaided eye, which just seems crazy that you can see something like that on the surface of the sun, you know, without any other kind of gear. I mean, like, what makes these sunspots get this size on the sun, or is that another one of those solar mysteries? Well,
it's a mystery, and it's not a mystery, and it's, you know, it's one of those situations where we understand the general things of what's happening. We don't really completely understand the exactly the physics. But yes, I went outside today. I put on my safe solar viewing glasses, which are basically eclipse glasses. And something for people to note is that if you do have eclipse glasses, they're not just good for eclipses. They're good for walking out and safely looking at the sun. It's the only time you can safely look directly at them is if you have the right kind of protection. But I went outside, and sure enough, AR 3310 is big enough that I can see it with my unaided eye. And that's actually not the biggest sunspot that we've seen. And in the last solar cycle, I remember doing a piece for my own website where I put up a comparison between one of the biggest sunspots at the time next to Jupiter, because in fact, the sunspot was huge. It was more than 10 times the size of Earth.
Wow.
And what's happening is the sun has all this magnetic field inside of it. And that magnetic field is getting twisted up over time. So the magnetic field starts kind of straight, going from the north to south pole. And the sun itself is not a solid body. And so just like the big gas giants like Jupiter and Saturn, when it rotates, because it's not solid, it rotates faster at the equator. And so the same thing is happening on the sun, and the sun's material is a plasma. So it's basically an electrified gas that interacts with electric and magnetic fields. And what that means is when the sun is spinning, it pulls the magnetic field with it. And because it's spinning faster at the equator, that straight magnetic field is pulled more in the center. And so over time, it's getting twisted up, almost like knotting a rope or a rubber band. And those knots pop through. So over the solar cycle, more and more of that magnetic field is concentrating. And so bigger and bigger knots are popping through the solar photosphere. And those big knots of magnetic field are the sunspots.
Wow. So I have a question. There's a follow-up. I'm sorry. This might sound like it's like out of left field, but you mentioned the sun's surface and that it's like this plasma. And I'm just wondering if it wasn't going to burn us to death and I could like touch the sun, would it be like squishy then? Or would it be like touching a cloud? Just like a really hot cloud?
It would be, well, it's really crazy to think about it, but the sun's surface is less dense than our own air. And it's kind of mind-boggling. Now, as you go, farther and farther down, closer to the center, it gets more and more dense, and it eventually gets to the point where it's many times denser than water. But the sun's photosphere, and especially the corona, the density is super low. As a matter of fact, if you took like a square box and you had the corona inside of it, and that's actually the part that we see during a total solar eclipse, you would only have maybe one particle inside of it. And it's crazy to think about it. So if you put your hand in it, even though the corona or the photosphere, which is 10,000 degrees, the corona is crazy, it's actually millions of degrees, you wouldn't feel it because there are not enough particles hitting your skin to transfer that heat.
That's so crazy.
It blows my mind when you think about it,
So I can't really touch it, even if I wasn't going to burn me to like crispy bits. But so you mentioned that the sun can have these even ginormous sunspot. It can have big storms. Should we be afraid, I guess, of this space weather? You mentioned earlier that it can affect our satellites and whatnot. And I know that Congress has even had hearings about the dangers of solar storms and what it means for us. And what are those dangers? And we could actually, this is a good time to maybe even talk about that Carrington event from 1859.
So let me step back and go over kind of the basics again of space weather. So we start with a sunspot or with a magnetic field. And when that magnetic field gets complex enough and twist it enough, I mean, again, kind of like a rubber band, you take a rubber band and you twist it enough, it's going to snap. And magnetic fields, there's something very similar happens, and they release that energy very violently. And they create the flash of light, the solar flare, and they push all that material out into space, the coronal mass ejection. And both the solar flare and the coronal mass ejection create huge shock waves, much like a sonic boom of a jet. And those shock waves push solar particles to super high speeds. And that actually creates this storm of what we call, solar energetic particles, relativistic particles. So those are sort of the main parts of solar storms: the flare, the CME, and then the particle storm. And each one of those has a similar, and some of them have different impacts. So the flare does a couple of things. The flare heats up the atmosphere. So the side of the Earth that's facing the sun, when that flare hits it, it will cause the atmosphere there to heat up. That changes the properties of the atmosphere, and that will impact communication. So it will disrupt certain radio signals. It can disrupt GPS to make it less accurate. But it also causes the atmosphere to swell. It expands. And so if you have a spacecraft here's a spacecraft, it's sitting, the other way around. So here's a spacecraft, it's sitting above the atmosphere. It's very low, very low density, but the atmosphere expands. All of a sudden, the spacecraft is experiencing more atmosphere, more drag, and that can cause the spacecraft to deorbit.
Didn't that happen to SpaceX? They lost a batch.
Exactly. Yes, that's exactly what happened. So SpaceX launched these Starlink satellites, and the Starlink satellites also are very tiny. Okay, so they're very, very tiny, which also makes them more susceptible to the atmosphere. And they start off in a very lower orbit, and then they go to a higher orbit. And what happened was we had a bunch of solar storms back to back. That the storms themselves were not huge, but the combination of, and in this case, actually the combination of not just the flare, but the CME, the geomagnetic storm, both of those caused drag, which I think it was something like 30, maybe 35 of those little satellites burned up.
Yeah.
And so that's happened to big satellites. And that's why it's very important for us to study, because what they do when satellites orbit is they predict, what's the atmosphere going to be like, and that determines how they're going to control the orbit. And so if space weather comes, that changes your estimates of what the atmosphere is like, and that changes your calculations for the orbit. So you have to have a good understanding of what's going on there. So that's one of the impacts. Now, the CME, when it reaches Earth and it disrupts the magnetic field, it creates all these electrical currents in the upper atmosphere. That creates this geomagnetic storm. Okay. And that geomagnetic storm, that's what gives us the aurora, because that then takes these particles from the magnetosphere and funnels them into the poles. They hit the atmosphere, and oxygen and nitrogen will get excited and glow. Oxygen gives us green, red colors, and nitrogen gives us kind of a bluish color, and then combined they give us, all these crazy colors. But what's also happening is that geomagnetic storm and those currents can themselves disrupt communications. Okay. And they can, in the strongest case, they can actually create currents on the ground. And so what's happening is, if you have a magnetic field that's changing and it's near a big conductor, it can induce electric field in that conductor. Okay. And that's a property of electricity and magnetism. That's the same property that helps us create generators and motors and things like that. And the ground itself is a conductor. So when then there are electrical currents up high, they can induce currents in the ground. But we've made these giant conductors, power lines, large power lines are huge conductors. And so if those currents are strong enough, if that storm is strong enough, that creates currents in the power lines. And power lines are not made to have that extra current going through them. And that can short out the power lines, which means we're going to have a blackout. And if it's strong enough, it heats up transformers and it burns them out, which is going to be even worse than just kind of tripping the circuit.
And that sounds familiar too, right? Because I remember there was a solar storm in the 80s, right?
Yes.
That affected power companies in Canada. Is that right?
Yeah, it was Quebec. Yeah, so Quebec. We call it the Quebec event. So it's 1989. It was a huge storm. It was a very, very active solar cycle, and that created a storm which knocked out the Quebec hydroelectric power grid. But the impact actually came down into the U.S. So New Jersey and some northern U.S. states experienced some of this activity. And there was a transformer. I've seen pictures of it. A transformer in New Jersey that was melted.
Oh my gosh! And then this is an example of how that could affect us today. But you mentioned the Carrington event. And that was again back in 1859. Now there weren't the power line infrastructure that we have now in 1859. But what happened then?
Well, so then, we didn't have the kind of infrastructure, electrical, and technological infrastructure. However, the most important way we communicated at the time was a telegraph. Okay, and so there were telegraph lines all over the globe, and so those were long conductors. And the Carrington event was, in some ways, we might call it the perfect storm. So what happened was there was a giant sunspot. It was very active, and a gentleman named Richard Carrington, he's a British astronomer, was studying the sunspot, and he's got these really nice drawings of it. And what he noticed was all of a sudden, when he's looking at the sunspot, the image went blurry. And what happened was it was a solar flare that was visible in white light. And that's an interesting thing in itself, because typically solar flares are mostly, they create light over the whole spectrum, but they're mostly bright in things like X-rays and gamma rays and ultraviolet. So that meant that it was what we call a white light flare. We know today that a white light flare is a very, very strong flare. So he noticed that, and then a couple days later, all of a sudden, the globe has all these stories of aurora. People are seeing aurora down in Cuba. People are seeing aurora near the equator. I've heard stories or read stories about cowboys that went out. Well, they woke up early thinking it was dawn because the aurora was so bright. So there are all these amazing stories of all this aurora all over and very, very close to the equator. Because remember, these storms are typically centered around the poles, but the stronger they are, the farther south they'll go. Mm-hmm. And so this is when this connection was made. Hey, there's this eruption on the sun. We saw this flare, and a couple days later, we had all this aurora. This is connected, And so what happened was there were at least two large coronal mass ejections. So the first one kind of swept through the solar system and cleared the way. And then another big one came after it. And it was, there was not a lot of material in the way, so it was able to travel much faster. And estimates are that it maybe reached the Earth in somewhere between 15 to 17 hours, which is super fast for one of these.
92 million miles an hour, or 92 million miles, right? To between Earth and the sun. And
so it's just crazy how fast they were traveling. And it created magnetic disturbances. We did, in fact, have magnetometers around the world. There was some famous ones in India. There's some in the UK. And the magnetic disruption was so strong that it went off the scale for all the magnetometers.
Wow.
And we've now estimated, not directly, that this was one of the largest storms, certainly in the last couple hundred years, and it's come kind of the standard candle for a superstorm.
Mm-hmm. Now, I wanted to ask about that going forward, because you mentioned, so now we've seen how the effects that space weather can have, the sun's weather can have on the surface of the Earth. We saw it in orbit. And of course, NASA wants to send astronauts back to the moon. They've done that before. Mm-hmm. And you've mentioned that it can impact astronauts in space. So I guess it's like a kind of a two-parter is how, because I would imagine that radiation is like the big issue from these events for astronauts. So, what are the risks for those astronauts? And then what sort of things do we do to track it so that we can tell them, hey, maybe today's not a good day for a moonwalk because of the sun?
Exactly. So in those types of space weather that I mentioned, the last one that I talked about, the particle storm, okay, those super relativistic particles. So those are particles such as electrons, that come from around atoms, or protons that come from in the nucleus of atoms. Those particles are accelerated to near the speed of light. And that's what we're worried about for astronauts, because those energetic particles are carrying so much energy that they penetrate when you're outside the protective layer of the atmosphere. Fortunately, they don't make it through the atmosphere. The atmosphere is very thick, and that's good for us. But once you're outside of it, you're no longer have the protection of the atmosphere and the magnetic field, which is also providing some protection. And so astronauts are being exposed to high energy particles, high energy radiation. And those particles are what we call ionizing particles. And that means that when they go through our cells, they damage our cells and damage things like DNA. They create radiation poisoning. And so this is what we're most concerned about for astronauts. And, as you mentioned, if you're going to go out for a spacewalk outside the space station, you want to know, is there a lot of activity? Because I don't want to be outside when a solar storm is coming, because those particles, while they're not traveling as fast as light, they can get here, 15, 20 minutes, because they're really close to the speed of light. And that's not a lot of time to get back inside, okay? Because it takes a while to get out there. They're out there for hours and hours and hours. And so we want to monitor the space weather and have some understanding of when those particles are going to come, because they don't always happen. And one of the things that you can do is, if you're in the space station, there is a lot of material in the space station, and there are places where there's more material than others. And the best way to stop particles is by having material between you and the particles. Mm-hmm.
So like shielding.
Yeah. Right, exactly. Yeah. And, ideally, we'd love to have concrete walls and lead blocks, but you can't do that in space because that stuff is too much mass. And so it's too expensive to put that stuff in space. But we can put a lot of materials. NASA has done a lot of work developing different types of polymers that do a good job of, shielding some of these particles. But then the question is, well, how do we know when they're going to come? Mm-hmm. And this is when we go back to, first of all, the sunspots. If you have a big sunspot and that sunspot has a good chance of producing a very large solar flare, that means the chances that it would produce one of these particle events is very high. We also know the CMEs can produce them. So CMEs, if it's a large CME, the same thing can happen. Now, the problem that we're faced with is it's very hard to predict if a sunspot is going to erupt. And we don't really understand that physics well enough to say, that sunspot is going to erupt tomorrow and give us this kind of event. Mm-hmm. So what we have to do is I think this is very similar. I'm not a meteorologist, but I think this is very similar to the way when we look at our weather maps and it says there's a 70% chance it's going to rain tomorrow. Mm-hmm. You look at the conditions, let's say the conditions today, and what were the conditions like in the past when it rained. So that gives you some idea of the percentage. And the same thing with sunspots. we look at the shape of the sunspots, we look at the magnetic field of the sunspots, and we look at past sunspots that are similar and see how many times did they produce a flare of a certain size. And that allows us to kind of calculate a percentage. So, that's not great, but that's kind of the first step.
And you mentioned monitoring, and I think this is a good time to mention that. I mean, it's not like no one's tracking the sun, right? I mean, there's a lot of satellites. There's the Solar Dynamics Observatory, the SOHO with ESA and NASA, and the Deep Space Climate Observatory, plus of course, all of the solar telescopes around the Earth. So, and there's a space weather prediction center that NOAA, you mentioned them earlier, that I get daily emails from them.
So so do I. I get daily emails, daily texts from them. I look at their site every day. There's a couple of, this is a very important point. All of these specific industries and, audiences that care about it are monitoring it. And where do they go? Well, space weather at Earth, space weather that impacts us here on Earth, space weather that impacts around the Earth, that is specifically the duty of NOAA, and it is the duty of the Space Weather Prediction Center. They are part of the National Weather Service, and so part of their job is to do these daily estimates, predictions. When a CME happens, they run a computer model, just like when we run computer models to tell us when a hurricane, when is it going to reach landfall, how big is it going to be. They do the same thing for CMEs. They create their own CME, maps, and they monitor all these different activities, and they put out warnings. They put out, a watch when something looks like, hey, this sunspot looks angry. It's gonna do something soon. And they work very closely with other agencies like NASA. So NASA has a couple of roles too. So NASA's not focused on being our watchdog for Earth, but what NASA does is scientifically, NASA develops models. And so NASA works with scientists around the world to develop, better models all over the heliosphere, which is sort of the domain of the sun through the solar system, and from the sun to the Earth. And eventually, when those models become reliable enough, those models are then used by an agency like NOAA, which we call operational. So it goes from research to operations. And so, but NASA has their own spacecraft all through the solar system. So not just ones around the Earth, but, Parker Solar Probe, which is flying around the sun, or Stereo, which is orbiting, or Discover, which is sitting out 1 million miles away. So NASA is responsible for that. That's not NOAA's job. So that's where NASA actually must do their own kinds of predictions. And ultimately, they're going to be doing this for the moon. They're going to be doing it for Mars. And we work with other agencies. So the UK has the Met Office. Korea has their own space weather agency. So lots of different science organizations around the world all monitor it. And then there are all the geeks like me who not only monitor it for work, but we're excited and curious about it. So we're looking at it all the time.
Yeah, we should mention that your website is The Sun Today, and that everyone should go check it out on if they want to know what's going on with The Sun Today. It's literally in the title there. So, thanks so much. I did have to ask, because I have you here and we've got a few minutes left, that the sun is not just a star for Earth, but it's also a star in Hollywood. And there've been at least a couple, if not more. I'm sure there are more, but there are a couple that stick out to me about like the sun being like a destination for us. There was Sunshine,
yeah,
where the sun is going out. And we have to, it's up to Earth to send a bunch, I guess, like a mountain of nuclear weapons to blow it back up so we can start doing that again. And then there was Knowing. Which with Nicolas Cage, which, by the way, I apologize if it's a spoiler alert, because he keeps thinking, but there's a disaster. And you find out at the end of that movie that it was a super flare. So I have to ask you about these two depictions of the sun and what your thoughts are as a solar scientist, because they get real close to the sun and sunshine. They see a Mercury transit. It was gorgeous, and then it turned into a monster movie. But
So I have to. I have to admit that I haven't seen Knowing, and I should see it because I'm a sci-fi. I'm a sci-fi nut. You may have noticed all the signed pictures on the wall behind me. So I do need to watch it, and I think I just gotta buckle down and do it. I think what I've understand. Well, sir, if they're not, as far as we know, there's not going to be a super flare which destroys the Earth. Okay.
Okay. I was worried about that. So
now we could have a CME that is as big as the Carrington event or even bigger. It's possible that it could be bigger, which could wreak havoc on our technology. It's not going to destroy our world. It's not going to destroy civilization, but it could cause a lot of damage, which could be expensive. It could be, cause a lot of problems for us. So that's a reality, just like it's a reality that a big hurricane can come hit you at your home in Florida, and it can cause a lot of damage, you know. But so Sunshine is a very cool movie. Unfortunately, like you say, it kind of turns into a slasher movie towards the end, but I think it's pretty cool. I don't know exactly. It's been a while since I've seen it, so I don't know exactly how, realistic some of it is, but I think it's pretty well thought out, The
TLDR is that they send a mission to drop a giant nuclear bomb into the sun to restart nuclear fusion because it's going out. So
now that part, I don't know how that would happen. So, nuclear fusion is not going to stop on the sun anytime soon. I mean, it's a whole nother discussion about the life cycle of the sun because, if you have nuclear fusion, it turns hydrogen into helium. When the sun uses up all its hydrogen, then it starts fusing the helium, and you start fusing bigger and bigger elements until you reach a point where it can no longer fuse anymore. You actually reach iron, which you can't. Iron is special in that it doesn't actually produce energy anymore. It's very, very different. And then the sun does some weird things that it'll actually bloat up, turns into a big red giant, and then it will expel that big outer part. What's left in the middle is a what's called a white dwarf, and then we get these planetary nebulas. So there's really cool nebulas that you see, planetary, like the Ring Nebula. That's kind of what's going to happen for the sun.
I would say don't tell your 5-year-old that the sun is going to swell up and engulf the Earth. In 5 billion years.
Probably not. Yeah, probably. But you can say, hey, we got a lot of time. So
I did learn that the hard way and had to explain what would happen to her toys and what would happen to the pictures on the wall. So
I saw the movie Finch. That's actually not too bad. I mean, it's a little too much, but it is kind of interesting.
Finch, Tom Hanks movie. He builds a robot.
Tom Hanks movie. Yeah. But I did want to say that one of the things to mention to folks is we do have some eclipses coming up. And so it is an opportunity. Right. The one in October 14th is an annular eclipse. So that's the one where you still have to wear your protective glasses no matter where you are. But really, the one that's going to give us the amazing show is, much like 2017, is April 8th, 2024. We're going to have another total solar eclipse across the U.S. And those who are in the path will see a longer eclipse, will have more totality, and the path is wider. So that is a really unique opportunity, if you're lucky enough to be there, to see the corona with your own eyes safely.
Better than a sci-fi movie. So I'll just reiterate that you just said April 8th, 2024. It'll be during spring break for at least my daughter. Yeah. And be thinking about it now, all you sun fans out there, because it's going to go northeast from Texas, San Antonio-ish, all the way up through Maine. And for a lot of us here, that's not a far drive inland a little bit to go check it out. So maybe I'll see you there, Alex.
I'll be in Texas, so you should come down to Texas.
Great. Well, we will keep that in mind. Well, Alex, thank you so much, Dr. C. Alex Young of NASA's Goddard Space Flight Center, for talking about the sun, giving us, shining a ray of light, if you will, on the sun itself.
It's been a pleasure. I'm always happy to talk to you because there's so much we didn't even get to, So.
I got the crickets again. No, there is so much. There is so much that we could have talked about. You mentioned just the life cycle alone. So we'll definitely, if you want to come back on again, we're going to ask you about that too.
I would love to. Yeah.
But where can folks keep track of the work that you were doing, of NASA doing to monitor the sun and let us know what's going on today?
Well, so a couple places you can go to nasa.gov and then just go up to the top for missions and look under what's called solar system and beyond, and that gives you the sun. Or you can go to science.nasa.gov and look under the Helioscience Division. And all of those are going to tell you about the research we're doing through the whole solar system, about the missions like Parker Solar Probe and Solar Orbiter, and all of the amazing stuff. And not only what's happening in heliophysics, but how does that connect with astrophysics, planetary, and earth science? Because they're all connected to each other and they're all important. And it's great to sort of see that bigger picture.
Well, we'll definitely check that out and make sure that we've got those links in the show notes below. And of course, you can find me as always at space.com and on the Twitter at Tariq J Malik. J this week stands for just chilling with the sun, I suppose. And of course, you can find Rod back here next week, which would be really great. But don't forget to drop us a line at twit.tv. That's TWIS at twit.tv. And we welcome your comments, suggestions, and ideas. Don't forget those space jokes as well. And we love getting your comments, and we try to answer each and every message that we get. And of course, you can check out space.com. The website's in the name. And Rod's alma mater, the National Space Society at nss.org. They're real busy right now at that International Space Development Conference. And they're both great places to get your space fix. New episodes published every Friday on your favorite podcatcher. So please make sure to subscribe and tell your friends and give us reviews. 5 stars would be great, or 5 suns, I guess I should say, for this episode. And a thumbs up would be nicely. So thank you so much. And you can head to our website at twit.tv/TWIS. And do not forget that you can get all of the great programming on the TWiT network ad-free at Club TWiT, as well as some extra stuff like me falling off my chair, which Rod likes to point out every single week. Or I did spill coffee on myself a couple episodes back, if you were able to see that. It's $7 a month, and you can follow the TWiT Tech Podcast Network at TWiT on Twitter and on Facebook, and of course at twit.tv on the Instagrams and the internet. So thanks so much for all of your time, and we will see you all in the next one.
If you love all things Android, well, I've got a show for you to check out. It's called All About Android, and I'll give you 3 guesses what we talk about. We talk about Android, the latest news, hardware, apps. We answer feedback. It's me, Jason Howell, Ron Richards, WinTwit Dow, and a whole cast of awesome characters talking about the operating system that we love. You can find All About Android at twit.tv/AAA.